All right, let's dive deep today. We're going deep into the Java virtual machine,
The
the
JVM.
JVM. It's the magic. It's what makes Java code run on, well, anything.
Yeah, write once, run anywhere. That's the beauty of it.
Exactly. From your phone to a massive server, it all comes down to the JVM. And today we're gonna crack it open and see what's inside.
We'll be focusing on the architecture, how it's all put together, and then the memory management piece. How does the JVM actually handle all the data?
You'll finally learn what bytecode is.
Yeah.
You know, how the JVM actually understands your Java code.
And we'll talk about the JVM's own memory, the stack, the heap. It even has garbage collection.
Yeah, the JVM cleans up after itself. It's pretty neat.
Keeps things running smoothly.
And by the end of this, you'll really appreciate how this design makes Java so secure and robust.
It's a fascinating piece of software. It really is like a virtual computer.
Okay, so let's unpack this virtual computer idea.
Yeah.
What's the JVM's architecture actually look like?
Think of it as a layered system. At the
Okay.
top, you have your Java code,
Right.
which the compiler translates into bytecode.
So that's the translation step. My Java code becomes bytecode, and that's what the JVM understands.
Exactly. And then this bytecode enters the JVM, which is where the magic happens. You
Yeah.
have the class loader that brings your Java classes into memory, ready to go.
Okay, so the class loader is like the librarian fetching the books, or classes in this case,
Exactly. Then we have the execution engine. That's the heart of the JVM.
the brains of the operation.
It reads and executes those bytecode instructions. And finally, we have the runtime data area. That's where all the data your program needs lives. Objects, variables, all that stuff.
So the execution engine is like the brain, and the runtime data area is like the memory of our virtual computer.
Perfect analogy. And this runtime data area is actually divided into several sections, each one with a specific purpose.
Oh, so it's not just one big blob of memory, it's organized.
Absolutely, very organized. We'll be focusing on three key areas: the method area, the heap,
Okay.
and the Java virtual machine stacks.
So it's like a well-organized filing cabinet for all the data the program needs. Tell me a bit more about these sections.
Sure. The method area, that stores information about the classes loaded into the JVM, including the code for your methods. It's like a blueprint of your entire program.
Right, so the method area is where the JVM keeps track of the overall structure and instructions.
Yep. And then you have the heap. That's the largest section of memory. That's where objects live.
Okay, so when I create a new customer object in my code, it goes into the heap.
Precisely. Think of the heap as a dynamic storage area, constantly growing and shrinking as objects are created and removed.
Wait, so objects can disappear from the heap. Doesn't that mean the data is lost?
Well, that's where things get really interesting. The JVM has this built-in mechanism called garbage collection. It reclaims memory occupied by objects that are no longer needed. But we'll talk about the garbage a little later. First, let's finish up with the last area of the runtime data area, the Java virtual machine stacks.
All right, let's stack them up. What are these stacks all about?
So every thread running in your program gets its own stack. It keeps track of what's happening within that thread.
Okay, I'm thinking of like a stack of plates. Each plate is a method call.
That's a great way to visualize it. Every time a method is called, it's like adding a plate to the stack. We call that a stack frame. And this frame stores things like local variables, method parameters. When the method finishes, it's like taking the plate off the stack.
So it's a way to keep track of the flow of execution within each thread.
Right.
Make sure everything happens in the right order.
Exactly. This stack structure ensures that method calls and returns happen smoothly, no hiccups.
Okay, so we've covered the class loader, the execution engine, and these different memory areas. What else is there to this JVM architecture? Is there more?
There is. We need to talk about the instruction set, the actual commands that make the JVM tick. Remember bytecode?
Yeah, the JVM's language.
Right. Well, the JVM has this whole set of instructions that can execute from that bytecode. They cover everything from basic arithmetic to, complex logic operations.
It's like the JVM's secret code.
Think of them as low-level commands controlling the JVM's every action. Instructions for adding numbers, subtracting, loading, and storing data from memory, even instructions for controlling program flow.
So like if I have an if statement in my code, that gets translated into one of these bytecode instructions.
Exactly. The compiler takes your very human-readable Java code and breaks it down into these precise bytecode instructions. Instructions the JVM can understand and execute.
Okay, I'm starting to get the big picture here. We've got the class loader bringing in the classes, the execution engine running the show based on these bytecode instructions, and the runtime data area holding all the information. But how does my Java code actually become bytecode?
That's the job of the Java compiler. It takes your code and translates it into that bytecode that the JVM can execute. So let's say you have a simple loop in your code. The compiler will break that down, turn it into a series of bytecode instructions. Instructions for incrementing the counter, checking the condition, everything the JVM needs to run that loop.
This is really cool. It's like this well-oiled machine with all these interconnected parts working together to run our code.
And there's one more crucial piece we need to discuss: garbage collection.
Ah, yes. The cleanup crew.
Exactly. It's one of the JVM's most important features, and make sure our virtual computer doesn't run out of memory. But we'll dive into that fascinating topic in the next part of our deep dive.
Okay, so stay tuned. We're
Yeah.
going to get into the nitty-gritty of how the JVM keeps its memory spick and span.
So as your program's running, right, it's creating all these objects on the heap.
Right. Tons of objects.
And eventually, some of those objects, well, they're not needed anymore.
They've served their purpose.
Exactly. And if they just stayed there, taking up space,
The heap would get full.
overflowing, your program would run out of memory. It'd be a mess.
So it's like forgetting to take out the trash. Eventually, your house is overflowing with garbage.
Perfect analogy. That's where garbage collection comes in. It's the JVM's way of cleaning up the heap, reclaiming memory that's no longer being used.
That sounds incredibly useful. But how does the JVM know which objects are trash and which are still valuable? It's not like they have labels, right?
Right, it's not that simple. The JVM uses a technique called reachability analysis.
Reachability analysis.
Yeah, it starts from a set of root objects, things like active threads, static variables,
Okay.
and it traces the references from these roots to other objects.
This is like following a chain of connections.
Exactly. Any object that can be reached through that chain, through those references, it's considered alive, still in use.
Okay, so it's like a network. And the JVM is checking which objects are still connected to the active parts of the program.
Exactly. If an object isn't reachable, if it's not connected to those roots, it's considered garbage, ripe for collection.
And that's when the garbage collector steps in.
That's right. It reclaims the memory occupied by those unreachable objects, cleans up the heap.
That's pretty impressive. The JVM is doing its own spring cleaning, keeping everything organized and efficient.
Yeah.
But doesn't this garbage collection process slow down my program? I mean, pausing everything to clean up sounds like it could take a while.
It's a valid concern, but modern garbage collectors, they're very optimized.
Oh, okay.
They work in the background using all sorts of clever algorithms to minimize pauses.
So it's not like everything grinds to a halt while the garbage collector does its thing.
Not at all. The impact on performance is really quite minimal, especially compared to the benefits of having a clean and efficient memory space.
So it's a trade-off worth making. Okay, so we've got this whole system of memory management. The heap, the stacks, the garbage collector, all working together to keep our Java programs running smoothly. It's like a well-coordinated team. But how does all of this knowledge actually help me write better code? What's the practical takeaway here?
Well, understanding how the JVM manages memory can help you write better, more efficient code in a few ways. For one, it helps you avoid memory leaks.
Memory leaks, what are those?
A memory leak is when your program accidentally holds on to objects that are no longer needed.
Oh, okay.
And this prevents the garbage collector from reclaiming that memory.
So it's like hoarding old newspapers. They just pile up and take up valuable space.
That's a great way to put it. By understanding how references work, how the garbage collector operates, you can write code that avoids those memory leaks.
Right, keep things tidy, make sure your program runs efficiently, doesn't hog all the resources.
Exactly.
Are there any other benefits to knowing about the JVM's inner workings?
Absolutely. Understanding the JVM's architecture can help you optimize your code for performance.
Oh, okay. How so?
For example, knowing how objects are created and stored on the heap, that can influence your design choices.
Interesting.
It can lead to more efficient data structures, better algorithms.
So it's not just about preventing problems, it's about writing faster, more efficient code.
Exactly. Knowing how the JVM works gives you more control. It's like having a roadmap of the environment your code runs in, allows you to navigate it more effectively.
That makes a lot of sense.
Yeah.
But I have to admit, all this talk about bytecode, heaps, stacks, garbage collection, it can feel a bit overwhelming.
Mm-hmm.
Do I really need to become a JVM expert to write good Java code?
You don't need to be an expert, but having a basic understanding, a general idea of how the JVM works, it's incredibly beneficial.
Okay, that's reassuring.
Knowing the basics of memory management, garbage collection, the runtime environment, it can really impact your coding practices for the better.
So it's about having a solid foundation, not necessarily becoming a JVM guru. That makes me feel better. But I'm still curious. You mentioned earlier that the JVM provides security features. How does it do that? Does it have its own little security guards running around inside?
That's a great question, and it's a really important aspect of the JVM's design. One of the key ways the JVM ensures security is through its bytecode verification process.
Bytecode verification. So this is related to those bytecode instructions we talked about earlier.
Exactly. Before the JVM executes any bytecode, it runs it through a series of checks. Make sure it's safe, doesn't violate any of Java's security rules.
So it's like airport security screening passengers before they board a plane.
Exactly. The JVM is making sure no malicious code sneaks in and causes trouble. It checks things like, does the code try to access memory it shouldn't? Does it try to overflow the stack? Is it trying to call methods with invalid parameters? All these checks ensure that the bytecode is well behaved, doesn't pose a security risk.
Wow, so the JVM has its own security team constantly on the lookout for any suspicious activity.
You could say that. This bytecode verification process is fundamental to what makes Java such a secure platform.
Right, it's stopping malicious code from causing harm to the system or accessing sensitive information. That's a relief. But the JVM's security measures, they don't stop there, do they? There's more, right?
You're right. The JVM also uses a sandbox environment. It restricts the actions that Java programs can perform.
A sandbox.
Yeah, it limits their access to the underlying system resources. Think of it as a safe space for the Java code to play in.
Okay. But with clear boundaries to prevent it from causing any damage outside that sandbox.
Precisely. It's another layer of protection, ensuring that Java programs operate within a controlled environment.
That's really impressive. So far, we've covered the JVM's architecture, memory management, garbage collection, and these security features. It's clear that JVM plays a crucial role in the whole Java ecosystem.
And we've only scratched the surface. The JVM is a very complex and powerful piece of software.
Right. Lots of intricate details and optimizations.
But understanding these fundamentals is a great starting point for any Java developer.
Definitely. It's been a deep dive, but thanks to your guidance, I think we've all gained a much better understanding of what makes the JVM so special. What's next on our JVM adventure?
In the final part of our deep dive, we'll explore how the JVM achieves its famous portability. The write once, run anywhere magic that makes Java so versatile.
The magic. All right, stay tuned, everyone. We're about to uncover the secrets of the JVM's portability. Welcome back. So before we jump into the final part of our JVM journey, let's do a quick recap, shall we?
Sounds good.
We explored the JVM's architecture. Remember all those different parts working together?
The class loader, execution engine.
Exactly. And then the memory management system, the heap, the stacks, the garbage collector, keeping everything tidy.
Right, and how the JVM keeps our code safe with that bytecode verification process.
And the sandbox environment. So much going on inside this JVM.
It really is quite a remarkable piece of software.
Okay, so now, as promised, we're tackling one of the JVM's most celebrated features. It's portability. This is what lets your Java code run on, well, pretty much anything. Tiny embedded systems, massive servers, you name it.
Write once, run anywhere. That's the promise of Java.
The magic, right. But how does the JVM actually pull that off?
It's not magic, but it's definitely clever engineering. The JVM achieves portability through abstraction.
Abstraction.
It provides a consistent platform for your Java code, regardless of the underlying hardware or operating system. Think of it like a universal adapter.
Oh, okay. So my Java code can plug into any device as long as it has that adapter, that JVM.
Exactly. The JVM acts as a middleman between your code and the actual hardware. So you, as a Java developer, you don't need to worry about the specifics of different operating systems or hardware architectures.
So I can just write my code once, and the JVM handles all those nitty-gritty details. That's pretty amazing.
It is. It's one of the major advantages of Java, this portability. It makes it so versatile, suitable for all sorts of applications.
I can definitely see why it's so popular. It's like having a universal translator for software. But this JVM, I mean, it must be pretty complex to handle all these tasks. Managing memory, ensuring security, enabling portability, it's a lot.
It is a complex piece of software, but it's also constantly evolving. There are different implementations of the JVM, each with its own strengths and optimizations.
Different implementation.
Yeah, for example, the Hotspot JVM, developed by Oracle, it's known for its performance and its just-in-time compilation capabilities.
Just-in-time compilation. That sounds intriguing. What is that?
Well, it's a technique where the JVM, as your code is running, it analyzes it, and it identifies frequently executed sections. We call them hotspots.
The parts of the code that are getting the most use.
Exactly. And then the JVM, it compiles those hotspots into native machine code.
So it's basically making those frequently used parts run faster.
Much faster. It's like the JVM is learning from your program's behavior and optimizing it on the fly.
That's really cool. So my Java code is like constantly changing as it's running.
In a way, yes. The just-in-time compiler selectively compiles parts of your code to boost performance. This is one of the key reasons why Java, even though it's platform independent, can achieve such impressive speeds.
That's fascinating. So we have all these different JVM implementations, each with their own little tricks to make Java code run smoothly and efficiently.
And it doesn't stop there. The JVM ecosystem is constantly evolving. New features, new advancements, all the time.
Wow. Sounds like there's always something new to learn about the JVM.
There is. It's a rich and complex world,
Mm.
and exploring its depths can be really rewarding for any Java developer.
I think it's safe to say we've all gained a much deeper appreciation for the Java virtual machine today.
Yeah.
It's more than just a runtime environment. It's this sophisticated engine that powers the entire Java world.
And its influence extends far beyond Java itself. Many other languages, Kotlin, Scala, they also run on the JVM.
Wow, leveraging all that power and portability.
Exactly. It's had a huge impact on the software development landscape.
So as we wrap up this deep dive, what's the one key takeaway you'd like our listeners to remember about the JVM?
Remember that the JVM is your ally. Understanding how it works, even just the basics, can help you write better code, more efficient code, more secure code.
So embrace the JVM, explore its capabilities, and never stop learning.
That's the key.
Great advice. A huge thank you for guiding us through this deep dive. It's been an enlightening journey. And to our listeners, keep exploring, keep learning, and keep diving deep into the world of technology.